Welcome everyone to Steel for Lunch. Today's presentation is going to be on insights into life as a structural engineer. Our presenters today are Stephen Osterhoff and Dean Anderson from Dialogue and Steadfast Engineering, both members of the Steel Center. So as always, we'll take a couple of seconds to say thank you to all the Steel Center members for their efforts. And we'll also, I just wanted to let you know that we have two upcoming presentations. One is on explainable regression trees for construction engineering applications. So this is on the technology theme of our research or our focus here at the Steel Center. And this will be on June 4th. And the one after will be an overview of the renovation of the tower of the Montreal's Olympic Stadium. So that's going to be also an interesting one presented by WSP. And I forgot to mention, but the first presentation will be by Dr. Ming Lu. He's a new, we're working with him on a new project at the Steel Center, so it's going to be exciting to see some of his previous work as well there. So I'll introduce our two speakers today. So Dean Anderson is the founder of Steadfast Engineering. He worked on structural steel connection on projects across Canada with a variety of fabricators. For the past 14 years, he has an MEng in structural engineering and a bachelor's both from the U of A. And then we have Stephen Osterhoff, a longtime dialoguer. He first joined as a civil engineering student in 2006, also a U of A graduate. Steve has been involved in many of the iconic projects around Edmonton, whether it's the Ice District, the Enbridge Center, and in Calgary, the Calgary Cancer Center. With that, I think I'll just hand over to them and we'll take it from there. So I'll stop my screen and over to you, Steve.
Thanks, AJ. Great to be here. Great to see lots of familiar people around the Zoom screen, and yeah, excited to chat with you guys today. Dean gave me a call, that was probably a couple of months ago now, and he said, hey, want to present to the Steel Center for Steel for Lunch, and had this great idea to present about what we do every day, like what it's like to practice as a structural engineer. And Dean and I are both structural engineers practicing in kind of different areas, which we'll get into. And after he brought that up, I started thinking, you know, when I was in undergrad, I certainly didn't know what a structural engineer did every day. I was learning about it, but I didn't know. I knew I wanted to be one, but that was about it. And then that kind of evolved, and through co-op terms, you got like a little bit of exposure to how the construction process works and what your role was in that bigger picture. But no one ever like sat down and just talked about it and explained it to me. And I thought, you know, I know that all of the people on here have some interest in structural engineering, that we thought we'd just talk about what the process is and what our involvement is as structural engineers in it day to day. And so that seemed like a pretty easy thing to talk about, because it's just talking about what we do. So that's what we're going to try to do today. And yeah, Dean, any other thoughts on where we want to go?
No, that was really explained it really well. It is basically what I had the same experience when I was in undergrad. You learn all the theory, you learn how to do the engineering work itself. But as far as what you do for a job day to day, didn't really understand exactly what that would look like. So yeah, that's why I thought it'd be kind of good to talk about that a little bit, kind of talk about, you know, what you do day to day. You know, how does a construction project work overall? So hopefully we could shed some light on that. And I'm really glad, Steve, that you agreed to do this with me, because I think it's a good balance between the two of us. You're an engineer of record in a big company. I'm a delegated design engineer in a small company. You know, so we have kind of a good wide range kind of what different engineers might do. Because when you think of a civil engineer or a structural engineer, it's not just one thing. You know, you can branch out into a whole bunch of different fields depending on what the market can allow. So yeah, it's kind of nice. We're going to talk, yeah, about our respective jobs, kind of how we fit into the whole construction process. And then we're actually going to talk about a specific project that we worked on together back in 2015 and 2016. So we're going to get to that at the second half of the presentation. So, and again, if it's okay with AJ, if there's any questions as we go along, feel free to write them in the chat as we go, and we can look at those at the end. And hopefully we can answer any questions that you might have as we go. So I can hand it back to Steve, and he's going to talk a little bit about the construction process overall.
Yeah, here we go. So I tried to really put a broad overview on the life cycle of a construction project. And I'm sure you've all been exposed to this before, but every project starts with a planning phase where you really are just identifying what the problem is that you're trying to solve. And once that's identified and you have the scope of what it is you're trying to solve, you get into the design phase. And during design, the design progresses from a concept through kind of a schematic design phase. So you'll hear people talk about SD, DD, CD. What they're talking about is the progression of design from SD, which is schematic, to DD, which is design development, where you increase the level of detail, refine the information that you can do costing off of, and start to get a budget for your project, all the way to CDs, which is either contract documents or construction documents. Those are the drawings that are actually built off of. So that's the phases of design that you get involved in. And through those, there's extensive stakeholder engagement. So you'll have a client, the person who actually has the problem that you're trying to help them solve. So whoever owns the building, or whatever branch of government is responsible for the construction of a facility. So you need to engage them and make sure that as you're working through the problem, that you're aligning the solution with what they want. Often there's also public engagement to make sure that if you're having any impact to people external to the organization that's building it, that you can start to incorporate that into how you're responding to the design problem. And it's also important to point out that during this phase, there are a whole bunch of different disciplines involved, experts in their field. And it's a collection of different groups of people, from structural engineers to architects to mechanical engineers and civil engineers, geotechnical engineers, depending on the nature of your project, that come together, and you have to coordinate and collaborate to solve the problem. Once you get through design and you've figured out what you want to build, projects move into construction, where there's a role for the structural design engineer to be involved, again, to make sure that the thing that you've designed is built in a way that's consistent with all of the assumptions you made when you did the design, and that there's no gaps there. And at that phase, there's also some more design work that goes on. It's something called delegated design, which I'll talk about a little bit later. And then the last phase is after the building's done, then people start using it, and there's operation and maintenance. So I'm going to dive into each of these a little bit deeper. Structural engineers typically are involved at all the stages. Our involvement is most intense through design and construction typically. Planning sometimes happens with or without involvement from a structural engineer. Although I always advocate that the earlier you can have a diverse group of experts at the table, the better your planning phase will be, and the better you'll be able to define the problem with some diverse perspectives. But often the structural engineer gets brought in at the design phase, at the beginning of that concept design or schematic design phase, and then is involved all the way until the building's handed over. And then during operation and maintenance, often if there are things about the building that need structural input, like they want to cut a new hole through the floor, they want to make some structural modification, you'll often get brought back into the building to look at that as the engineer of record, or they could hire a different structural engineer to come and look at that stuff in the future. So that's kind of where we get involved. So again, I'm going to start back at planning and just explain a little bit more what our role is as structural engineers in each phase. So I put up this very simple diagram here, and this is what I would call the brief, or basically the big picture. What are we trying to solve? So here, what you're looking at is a piece of trace paper over Google Maps, and this is the White Mud Drive. And north of White Mud Drive, there's a whole bunch of shared use paths that come together at this node at 142nd Street. And south of White Mud Drive, there's these shared use paths, and there's no way to get across, right? To get from here to here, it's only 100 meters, but you actually have to go like 2 kilometers up around over 53rd, down by Terwilliger, and then go back into the neighborhood. So at a very simple level, the problem statement, the brief that you're trying to solve is to connect these 2 points. And I always, as a structural engineer, I try to understand what's behind the project. What's the thing you're trying to solve? And I think coming out of school, you're kind of trained to answer a question with a set of predefined parameters, right? Solve the size of this beam. Here's the load, here's the span, here's the, like all the different constraints that allow you to solve the problem are there. But what I found practicing as a structural engineer is that what you really need to understand is not that predefined problem, but what's behind that problem, because that's where you can start being creative and actually do engineering work. The calculations are a tool to solve the problem, but understanding what the problem is the real secret to engineering, because like sizing a beam is kind of easy once you find the right equation or build the right spreadsheet. Deciding whether there needs to be a beam or not, like that's the interesting question. So if you understand the problem you're trying to solve, you can ask those kinds of questions and actually design instead of just calculate a building or a bridge. So once you have a clear understanding of the problem you're trying to solve, you go into the design phase. And as a structural engineer of record, this is where the majority of my time day to day is spent. And this is everything from coordination meetings with other disciplines to detailed calculations to drawing preparation to checking drawings. All of those things are part of my daily life, building structural models of things, putting loads into them, getting designs out. I would say I spend more than half my day doing that kind of stuff, all related to this design phase. The progression of design, kind of from a concept to a detailed set of drawings that somebody can build. I really love this process. I'll illustrate it here. This is that same bridge that I just showed the overall problem statement for. And on the bottom, I kind of drew a free body diagram with, this is a bending moment diagram with the span arrangement, and figured out where the peak moments are, and then started to sketch up, well, what's a concept for a bridge that responds to this force, these forces along the length of the bridge. So very early, like I've got a pile of 20 of these, just sketching up different ideas for how to solve the problem. And then you kind of progress from this concept and sketch level to refining the concepts a little bit, refining your sketches so that it's something that people can understand and you can socialize with your client who's building the bridge, with the public who cares a lot about how this bridge looks because it's right in their neighborhood, with the other design disciplines, the architect and the civil engineer and the geotechnical engineer. So you start refining that and sharing that to better define the design that you're working on. This is a clip, I took it this morning from the City of Edmonton's website. And during the design phase, something that I didn't maybe appreciate until I started practicing is just the number of stakeholders that actually influence the work that you do. Again, you don't just get this, this question on an exam that says, design a bridge that has a 90-meter span and it's a steel plate girder. It's actually, there are a lot of variables that go into all the decisions that then lead you to that thing that you can calculate. So here's people's comments that live in the neighborhood saying, I like this design because, I don't like this design because, and they will think of things that you, coming from outside, don't know that really can influence your design. So then you take that feedback, you farther refine your modeling and your design till eventually you get to construction documents or contract documents, where every detail that's needed to build, for a contractor to bid on this, to say how much it will cost them to build it, and then eventually to build it, are on a technical set of drawings, like you see here. So then that is all done to get you to a place where you can actually build it. And this is at the heart of why I love being a structural engineer, this idea that you can have an idea and you can create something to solve a problem, but that it doesn't just live inside of the computer or on a drawing, but it gets physically manifested. And it is the coolest thing to work on a project for 6 months and to walk out on site and just see these massive steel connections that you've calculated the capacity of those bolts, and you've thought about how that structure will behave and deflect, and to actually see it built is, I don't know, for me, it's the ultimate job satisfaction and really cool. So our role as engineer of record, as a structural engineer, is to stay involved throughout construction. So we actually go on site. We look at how things are coming together. We address issues with unforeseen site conditions. We answer questions and make clarifications because, first of all, no set of drawings is ever perfect. And second of all, no set of conditions under which you're building are ever perfect. So you try to work together with the builder to solve some of those issues. And another important thing to understand, which I didn't really understand until I started working, was this idea of delegated design. And that's where Dean's role really comes in. And I'll let him explain what delegated design is and why it exists, and what his role as a structural engineer, a delegated designer, is on a project.
All right, thanks, Steve. Yeah, delegated design comes downstream from Steve's perspective. He's talking to some guy who wants to build something, or some group of people that want to build something. He's solving that problem to try to get that done. Then as it goes down the process, there's a reason that they have delegated design with respect to connection design, which is what we do at Steadfast, after a fabricator is hired. So this is down in that construction process. So the building has been, or the contract documents have been essentially completed, hopefully fully completed. Sometimes that kind of comes a little bit earlier, but hopefully those construction documents are completed. We have a full set of drawings, and they put those drawings out for tender. So different steel fabricators, the people that are actually going to build this, they're actually going to weld all the connections, put all the bolts in, put it up on site. They bid on the job, and they say, okay, you're going to pay us this much money to build this project. Several people put in their price for that, and one is chosen. And that connection design that's delegated to those fabricators is delegated out because different fabricators have different processes and systems and ways of doing things. I've worked with, I don't know, probably 100 different fabricators, and I'm still surprised when I think, based on my experience, that this is the way they're going to want to do it. They still say, oh, no, I don't want to do it that way. Like, that way's, doesn't suit my processes. Some of the examples here are some of these connections. On the two pictures on the left, we have one beam connecting to another beam. The far left picture shows what they call a double angle connection. So there's a piece of L-shaped steel called an angle that you can see, and there's another one of those on the opposite side. So if a fabricator has something called a beam line or a robotic cutter that can cut the top and bottom of that beam that's framing into that other beam, they're going to want to choose this because everything's automated in their shop and it's easier for them to do that. The connection just to the right of that is called the shear tab connection. So it's done a little bit differently. You don't have to cut the end of that beam, but you do have to cut the plate in a different shape and weld that in. And the bolts are a little bit different that way. So every fabricator has these different ways of doing things. And because of that, they don't want those connection designs done early. And they want their own engineer to do it so it suits their shop and suits their processes. On the right-hand side too, we have two brace connections. The picture in the third from the left shows a welded brace connection. So that blue beam connecting to that gusset plate underneath is welded on site. So they have one little bolt in there that's just to hold it in place, and then a welder has to go up on a ladder or a man lift, and he's got to weld the sides of that brace to the gusset plate. And the one to the far left is a bolted connection. So all they have to do is put it up, put a couple of bolts in. So everybody's got different reasons for this. It's interesting in the brace connections. It depends who's hired the engineer to do the design. If a fabricator has hired somebody or has hired us to do the design, say, and they're not erecting it, this is more of a political thing or maybe of a business decision, but they might choose the field welded connection because they have less work to do in their shop and they're going to push that work off to the guy who's erecting it. Whereas if somebody is both fabricating and erecting it, putting it up on site, they might choose the bolts because that's easier on site, easier to put up on site. You just put the bolts in and you move on. And all of these things have to be balanced. As the delegated design engineer goes, we have to talk to Steve. We have to talk to the engineer of record and make sure that all of those design requirements that he has in his overall design are met. And then we also have to balance that with the fabricator and also balance it with the architect a lot of the time to make sure that it looks the way that the architect wants it to look. So a lot of different things kind of to balance in this. And that's why this process is delegated down the line, is because all of these people getting involved more in the construction process as opposed to earlier on in the process makes it better for the delegated design engineer to do it at that stage. I've actually talked to some people about maybe changing that process. Maybe it's easier to have everybody involved. Kind of like what Steve was saying, the more experts you have involved earlier in the process, the better the project goes overall. And I think that's really wise for him to say that. That's one thing that if you have an erector, you have a fabricator that's brought in really early, they might be able to come up with a better way to solve that initial problem than what is talked about because they're not at the table earlier on. So it's pretty interesting. I think this step with respect to delegated connection design is one of the most important to sort out all of those details earlier on, this basic connection configuration. At this stage, this is similar to Steve when he's trying to figure out the best process, and it's all kind of just general ideas of how you're going to put this thing together. This is that process with respect to connection design. How are these things going to generally connect together? And we do the detailed design a little bit down the line once we figure out those general parameters that everybody wants to meet. That's one thing as a student coming out, I've seen that happen where they think they have the best way to do it. They go through all the design steps all the way through. And then they realize, well, no, I can't do it that way. So they got to do it all over again. And that might actually iterate 2 or 3 times, but it's always better to review, to communicate. Again, back to Steve's point about talking to the people first. I think that's one of the most important things to learn when you come out of school. You have all of this technical knowledge. You know how to solve the problems, to make a spreadsheet, to analyze the structure in all these different ways. But sometimes the most important thing, and I think it is one of the most important things, is you have to communicate with all those different parties involved to solve that overall problem, like Steve was saying. And one of the things that I think is very important to teach students as they're coming out is to be humble. Sometimes, and oftentimes, the guy who builds it, the guy who actually puts it together is often the best one to talk to about the best way to actually have it built. Again, with respect to connection design, if I talk to an erector or an iron worker, the guy that's actually up in the crane, he's actually swinging this stuff into place, he's going to have a way that he would like this thing to look. He'd like to have the bolts in this location, the plate in that location. He doesn't want to weld over his head because that's really tough to do. You know, all of these things, he can tell you a configuration that works really well. And the engineer doesn't always have the best answers to a problem. And communication is that key. ask for that configuration, ask these people who are involved in the project, what is the best way? How do you think is the best way to do this? And be humble in it. Understand that you might have an idea and you think your idea is great, but it might not be the best idea. And you have to accept that sometimes and be open to all these different ideas. Communication truly is key to, sort out the best solution to these overall problems, either the big overall problem like Steve was dealing with, or these little nitty-gritty problems. Delegated connection design is all about the millimeter, sorting out exactly the spacing of the bolts and how much weld, how big of the weld is. So all of those things, if you get that communication involved, it's really important to do that, to have that coordination with people to bounce ideas off each other back and forth. On the next slide, this is a little bit more down the line. So we come up with our configuration as a connection designer. The things that we create, once we figure out these connections, we have to communicate these designs to people. So we create sketches and we create what we call a connection map. And what I do is I take the drawings that Steve has created, the engineer of record has created, and I mark those up in just my PDF software. So I put on little marks and I say like BMO1. So on the left-hand side, you have a drawing with some red text on it. That's me writing on that drawing, saying that I want to connect this with connection mark BMO1. And then on a second page, I'm going to have a sketch. So that's in the middle of the screen where you have that pencil sketch. And that's going to show exactly how this connection looks. So again, it's down to the millimeter. You're showing exact spacings, plate thicknesses, weld sizes, all of that stuff's on the drawing. And it's kind of funny. This is one thing that it actually took me by surprise a little bit, is that, I don't know, I was kind of old when I went back to university. I was 10 years out of high school when I went back and got my structural engineering degree. And I got into that mindset that what you use in school or what you learn in school doesn't apply in real life. And I think some people have that mentality. And I thought it was so fascinating that in the engineering career, in the structural engineering career, and especially connection design, is like solving a CIVI 270 problem. You actually have to make a free body diagram. You actually have to figure out all these forces. Just like in Steve's sketches earlier on, where he's showing the bending moment diagram. You actually have to do these things, to solve your problem. So I thought it was awesome that you really learn, or the tools that you learn in school, you actually apply. And you have to write these things out. And again, in connection design, that's really what I'm doing is I get all those parameters. So I'll get some loading information from Steve or the engineer of record. You have all your beam sizes shown on those drawings. And then you do the calculations and you make a sketch. And our final answer, like you would have in a CIVI 270 problem, is that sketch in the middle. So it's kind of interesting to see how that works. The one difference, and Steve touched on this a little bit too, is that the design parameters are oftentimes not clearly set up. You have to make inferences. You have to make judgments based on the situation. And sometimes they're not designed or defined initially earlier on. And some of the time, and actually more often than you would think, they're changed as the project goes along. Something will alter, something will change, and then you have to redo everything that you just did. So kind of interesting to see how all that works. So what we do, we make our sketches, we make our connection map, and then we bring in what they call a detailer, a steel detailer. That's a specialized draftsman, essentially. And they create a three-dimensional drawing or a three-dimensional model of what's happening here. So that's the picture on the bottom right. So we have the sketch in the middle, and then that actual connection is shown in the model on the right. So if we go to the next slide, we give this information to this detailer. So the connection designer makes his map, makes his sketches, give that to the detailer, the draftsman. He takes those things and he makes his three-dimensional model. So that's the picture on the right. Just so you know, this is what we're going to look at as our case study later on. These are the drawings from that project that we're going to look at in a little bit. So he makes that three-dimensional model, and the software creates a two-dimensional drawing from that model that he creates. He does this. We communicate on the way. Again, communication is key to this whole process. The detailer has a question. Maybe you misunderstood something. Maybe you didn't quite get how the geometry of something worked out based on the two-dimensional drawings that you're working off of. He's going to ask questions. You're going to collaborate. You're going to figure things out, and you're going to come up with the connection based on that. So he creates those two-dimensional shop drawings from that model, and they're called shop drawings. So Steve was mentioning contract documents, structural drawings from his side of things. The shop drawings that are created from this process are something that somebody in the shop, so the name shop drawings, can actually take that drawing and build this thing. So everything's, again, down to the millimeter. Every weld, every bolt, every dimension is shown on this thing. So a guy can actually make this in his shop. So he makes these drawings and then he sends them out for approval, they call it. So there's 2 stages for shop drawings in a construction project, generally. They have issued for approval. So this is the chance where all of the different parties that are involved can look at those drawings and say, hey, maybe this is right, or maybe this isn't right. And they can point things out that are either misunderstood or maybe not shown correctly. So the engineer of record, so like Steve, the architect, they send them to me as well as the delegated design engineer. We'll review these drawings in detail. And especially the connection designer is going to review these in full detail because that is their final product that they are going to stamp. So when I put my little beaver stamp in Alberta on this thing, I'm saying that everything on the shop drawings meet Alberta building codes. So these are going to be strong enough, it's going to be safe, and everything works. So they issue these things for approval. People have their chances to kind of look at them and make any changes as required. And then they make those changes, and then they issue these shop drawings for construction. So that's the IFC shop drawings. And that's that final project or final product that I would seal. That's something that I would seal or make a letter referencing saying all of these drawings look good. And these drawings, they're in such detail that there can be a lot. There's projects that I've done that have had 6,000 shop drawings that I've had to go through and review and make sure everything on there is correct. Every weld is right. Every bolt's in the right spot. So it's takes quite a bit of time. In my job, generally 40% of my job is doing the actual connection design. 40% of my time is checking shop drawings because there can be a lot of them. And then the other 20% of the time is generally just administrative stuff. So you're answering emails, you're going to meetings, you're talking about sales, you're making estimates, doing those sorts of things just with respect to the business. So that's how delegated connection design fits into that whole process. We're like one little chunk in the overall process of a construction project, but that's how we kind of fit in. So now we're going to go to a real project. So again, this is what we're looking at here. Steve's going to go into how this whole thing started because this is something that we worked on together back in 2015 or 2016. So I'll hand it back to Steve.
Yeah, awesome. I'll just go back one slide actually, as you're talking about shop drawings. Shop drawing review is also a big part of our life during construction, which Dean talked about, like it's sent to the engineer of record for review. The reason is that we are still taking overall responsibility for the structure as the engineer of record. So even though we delegate away the connection design so that it can suit whatever fabricator is actually building it, which we don't know when we're designing, so that it can suit their processes, we still need to do a detailed review to make sure that nothing is lost in translation, because our process of design was done without Dean there. And so if we made an assumption somewhere that we didn't explicitly state on the drawings or was misinterpreted or lost, we have to look through and make sure that the way that we assumed all the forces flow through the structure is consistent with how it ended up being connected. And so we'll end up marking those up and asking questions and really making sure that the design that was done downstream from us, it satisfies the requirements that we had in mind when we sent the drawings out. So if you ever hear about shop drawing reviews, like Dean said, I don't know if I've seen 6,000, but I've for sure seen shop drawing sets that are approaching 1,000 drawings, and it is quite intensive, the review process. So this project, it's a fun one. I've presented on this before when it was first built to probably some of the same people on this call, but we're going to zoom in specifically to the Pedway that connects this office tower that was built, back probably about 5 years ago. And we're going to look specifically at the Pedway and try to walk through kind of like what our role was as structural engineers on the design and construction of that Pedway. So kind of thinking back to that construction process I talked, or the process of a typical construction project, that the big idea here, that the concept, the problem we're trying to solve is that we're building a new office tower. And the tenant that was leasing up that office tower also had a lot of offices in the Manulife Place across the street. And as you know, a lot of downtown Edmonton is actually connected with Pedways, so that you don't have to leave the buildings to get from one to the other. You get all around downtown. You can even see in this image, there's a Pedway here. There's another one at City Center here, and this is the Pedway connecting this new building we were working on with this existing building. So very simply, the problem statement here, it's a pretty simple one, was how do we connect these two buildings? So we designed this Pedway. It's actually an interesting design from a structural perspective because it's what's called a Vierendeel truss. So a lot of Pedways you'll see they have diagonals, and they're either a Warren or a Pratt truss or something like that. But a Vierendeel truss has no diagonals. It carries load with vertical columns and horizontal top and bottom cords, and those have to be moment connected. So those connections typically on another type of truss would just be pin connections, transmit axial force only, but a Vierendeel truss works through bending through those joints. So we had a lot of really highly stressed nodes on the project, and those connections were delegated to the fabricator. Now, if you look at this is the final contract documents that went out for the job. At the bottom, there's a table there, and that table simply identifies the different members making up the truss, and then the connection forces. So moment and shear and axial force that connection needs to be designed for. So this is the information that we then passed on to the fabricator, which was Dean. Well, Dean was the fabricator's delegated design engineer.
Yeah, so we got hired by the fabricator to design these connections. We're happy to. It was a really good kind of project to work on. I like working on these interesting ones. You don't see a lot of Vierendeel trusses. It's kind of interesting to see this kind of configuration. So we were happy to work on it. And it was interesting with those high loads, those high forces. These wide flange members are actually pretty heavy and pretty thick, and actually quite small. So they're small and thick. So very interesting to design those connections to make everything work. So we got hired back in October of 2015. So this project is like 5-6 years old. I know it stretched into 2016, during construction. But one issue that we had with this. So on the left, you see the Pedway as a whole, and on the two sides, those are those Vierendeel trusses. You see, there's no diagonal bracing, so the two long sides. The fabricator had to build this. They had to erect this. So they had to figure out the best way to put this thing up. One of their parameters that they had to meet was that this spans over a road. So they have to stop the traffic on the road. They got to put a crane up. They got to build this thing. And the thing that they had to do was they had to block this road, build it throughout the night, and be done in one single night. So that was their challenge. And they had to figure out, okay, how are we going to do this? How are we going to make this work? And Steve can correct me if I'm wrong, but I believe at the time, those end boxes, the two little boxes that you would walk through at the end, those were fully rigid frames with no connections in them. And so for them to build this thing as a truss, or to build this thing on site, they have to split this thing down the middle essentially. So we had to put a couple of splice points in that end box so that they could put one truss up, put the other truss up, and then string all those little beams in between. Those all had to be bolted connections. So that's what we had to do. We had to sort out the way to splice this. The picture on the right, you can see what the final product was. We're going to look at it a little bit closer in a minute. But you can see those gray connections on the top beam and the bottom beam, those gray connections near the ends of those beams. Those are those splice connections that we had to come up with, and we had to figure out the way to do this. So this came up later. This thing was designed initially without those connections. So we had to say, okay, we got to put connections in there. So what's the best way to do this? And again, back to what we've all said up to this point, communication is key. Making sure you're figuring out the best way to do this. The next slide. This is a little bit of the back and forth that Steve had. So this kind of ties into a little bit about what real life is like as well as an engineer. So the fabricator comes to me and he says, hey, we got to put splices here. How do we do this? And I say, well, I need the loads. I got to know what those design parameters are because these weren't in that table that Steve showed. So we got to figure out the best way to do this. So on the top of this, if you see the text, that's an exchange between Steve and I. So one of several. So I sent Steve an email and said, hey, fabricator wants to splice this thing. He wants to splice it as close as possible to the truss. So he doesn't have these big legs kind of sticking off of the truss. So it's easier for him to ship and get to site. So what is the best place to splice this thing? And I talked about and kind of discussed where is the best place, because sometimes Some engineers are not so helpful and they don't want to give you the loads and they don't want to discuss things. I was very happy. Steve is awesome to work with, so he is willing to have this discussion. A lot of the time, they'll just come back and say, design it for full strength, because that's the safe answer. It takes 2 minutes to say that in an email, and then you're done with it. And that's something that, as a connection design engineer, I hate seeing the words full strength, because it's very difficult to design a connection for full strength. Well, it may not be difficult for me, but I know it's difficult for the fabricator. It's hard for him to build these things. They often get so big and convoluted because you got to transfer that full force of every part of that beam through the connection. So it tends to get really big and really ugly. So we wanted to know what the actual design loads were. So I asked Steve, where is the best place to do this? So what's the stress envelope diagram for this thing? So that's what he sent back. The attachment to his email is in the bottom part of this picture here. And it shows generally where the moments are. You know, the moment is kind of peaking at the joint, and it's kind of going down a little bit closer to the middle. So we went back and forth to figure out the best location for a splice. So kind of interesting how that all works. So on the next slide.
I'll chime in here. It's Dean's mentioned communication a couple times, and I mean, as a practicing engineer, it can't be overstated just how important clear communication is. And I was reminded of it again when Dean pulled this up. It's 2021, and there's a sketch I did in 2015. It was a good reminder of, I guess, for one, the permanence of your communication, right? This is on file as something that happened in the design, and so emails and sketches and all those things, they're part of you as a professional doing engineering work. So I was happy to reread it and see that I didn't write anything that I regretted 7 years later. But at the same time, I think it's just a picture of part of what it means to be a practicing professional is to work together to solve problems and collaborate. And Dean's right. It's actually very tempting to assume that you know better than the person down the line, whether that's the contractor or the connection design engineer, because the easy answer is like, go away, just do it and don't make me think about it. But the right answer is to find the best solution for the project. And I think that idea of humility is a really key one to how to practice as a professional and work together to do good work. So yeah, I appreciate that point, Dean.
Okay, right on. Yeah, the next slide here is the final product. So Steve and I went back and forth. We came up with the location. We came up with the loads. Well, Steve came up with the loads. Then I designed the sketch, which is the picture on the left, gave that to the detailer, and he put that in the model, and that's what was actually built. So that's the way they were able to do it. Steve can probably comment a little bit more about how the thing actually went up on site, but they were successful. It took them 1 night to build this thing and put it up. You know, they were able to put those trusses up on the sides with, I guess, a little bit of difficulty from what Steve was telling me before this presentation, but they did do it, and they were able to bolt all those members in between, and they only blocked the road for the 1 day. So it was successful that way. So it's kind of nice to be part of that whole process of, you know, being issued a problem that we both could work together to come up with a solution that did satisfy all the parties involved. You know, we have a solid structure. We have something that works, something that is brought up even now. Steve was mentioning too, you know, a couple of days ago when we were talking about how, you know, somebody went through the city and said, you know, we really like this Pedway. You know, we want our Pedway to look like this awesome Pedway, without the knowledge that Steve actually designed this Pedway in the past. You know, so it's something that lasts, something that works, something that looks really good, and something that was able to be built, you know, effectively. They were able to do it, and they were able to meet their goals. And it was really nice to be a part of that process to achieve that as a whole. And that's part of what it's like to be a structural engineer as a job. It's not just crunching numbers. It's talking with all the people to figure out the best solution for the problem that does satisfy as many people as possible. You know, everybody's got to give a little bit to come up with a compromise, but everybody can do that, and it can work. So it's really good to have people involved in a team that can do that to make something like this project, which was pretty successful. So I'll hand it back to Steve. He's going to talk a little bit about how the thing went up in construction.
Yeah, I will. And I'll kind of echo what you said about how the project turned out, Dean. I mean, we're always really glad when we see that Dean is on the job, because we don't know when we're going through it, but he's great to work with, and he gets it. He gets the process of collaboration it takes to build something the right way. And I remember on this specific job too, there's a lot of architecturally exposed structural steel. So the way that the connections looked was really important. We have glass wrapping the wall and the roof of this, and that corner connection was highly visible, architecturally exposed. And so the first round of shop drawings that we got, we reviewed together with our architects, and there was too many rows of bolts for the aesthetic that they were going for. And so I'd phone up Dean and say, hey, do you think we could use larger bolts, decrease the spacing, and shrink this connection down for aesthetics? And even though he had already designed it and drawn it, yeah, he said, yeah, we can do that. The forces will still work. And so that iterative process and that collaboration is what gets you to the finish line with a project that you can be proud of. And I guess, again, that attitude of working together, as opposed to saying, no, I'm already done, this will work, we can't do it that way, go away. So it's fun to work with people who want to do the right thing. Here's the truss going in. So this is construction. Again, you spend like months designing the project, thinking about it, going back and forth, and then it actually gets built and it shows up on site. And they erected the main trusses overnight. Dean mentioned there was some problems. I have time, I think, to tell this story. So we're going into two existing buildings, essentially. The Manulife Place is what you see there on the left, and then the new building that we had just finished building on the right, the Kelly Ramsey building, or Enbridge Center as it's called now. And so the anchor bolts to receive the bearings for the bridge, they were cast in on the one side 2 years earlier, before the bridge was even detailed or designed. But we figured out the anchor bolts and got them cast in. And as a rule, I don't give out my personal cell phone number to contractors because they will phone you like all the time. So I try to set up like clear boundaries on how we communicate and when. But in this case, I knew they were doing this big lift overnight. They had downtown shut down. So I gave my cell phone number, and it rings at 3 o'clock in the morning. I'm like, oh no, what's going on? So I pick up the cell phone, and it's the site super who's putting up the bridge. And he says, you know, man, we've been trying to fly this truss in for 3 hours, and we just can't make it fit. And the anchor rods that were cast in, the projection was too long, and they couldn't fly the bridge up over the anchor rods and then sit them down on top, because they were hitting the next floor of the building above, and they thought they could squeak it in, but they just couldn't. So we had to make the call in the middle of the night. We figured out that the anchor rods were weldable, which, as a side tip, is always a good idea, because it gets you out of a lot of jams, more than you would think. And there are lots of, you can put in non-weldable anchor rods, which would have just, I don't know, we would have been stuck. So in the end, we lopped off the anchor rods in the middle of the night, made sure there was enough left that we could, instead of putting a nut on to bolt them down, that we could get a weld in there later on, and we got the truss in. But yeah, here's a picture. This is still during construction. You can see they haven't put the cladding back on the supports, but this is what the Pedway looks like when it's mostly finished. It's wrapped. You can see there's the glass going over the roof. So there's those connections I was talking about, which were exposed and pretty important to the aesthetic of the bridge. And that's what it looks like inside. It's got this beautiful marble flooring, which is very heavy, by the way, which is part of why my members were so thick, Dean. But also, it actually helped us a lot, because we were worried about vibrations on this bridge too. That you could feel it bouncing up and down when there's a lot of people walking through. So having extra mass helps you with vibrations, because it takes more to get the structure excited. But yeah, that's kind of just a walkthrough of the construction process, start to finish, and the roles of us as the structural consultant and Dean as the delegated design engineer, and how projects get together. Maybe just a bit of a glimpse into what we do every day. And I hope it was helpful or interesting. I don't know, we've got some time here if people have any questions, or AJ, I don't know if you want to facilitate that, but yeah, that's kind of the end of our slide deck.
Awesome, lovely. Well, this was really interesting, actually. Thank you both, Steve and Dean. I think we'll be taking questions at this point.